the autoregressive memory bottleneck. To really understand why DiffusionGemma is such a game changer, we first have to understand the status quo, the problem that's basically plaguing modern large language models right now. Traditional autoregressor, or AR models, are fundamentally sequential. They generate text left to right, strictly one token at a time. It's literally like typing on a vintage typewriter. And because they have to constantly shuttle massive model weights into memory for every single word they generate, they are severely memory-bound. It's highly inefficient. Text diffusion models, on the other hand, they completely flip the paradigm. They process full blocks of tokens all in parallel. This shifts the bottleneck from being memory-bound to being compute-bound, meaning it actually utilizes the full processing power of the GPU hardware rather than just sitting around waiting for memory transfers.
Section 2. Decoding discrete text diffusion. Let's move to the solution and see how this builds on that new paradigm.
So how exactly do we fix that bottleneck and move to generative text modeling with discrete diffusion? Well, the core theory here relies on a continuous time Markov chain, which basically boils down to two main steps. Step 1 is the forward diffusion process. This takes clean, perfectly readable text and mathematically corrupts it down into pure, uniform noise. Step 2 is the backward denoising process. This is where the neural network learns to iteratively denoise that corrupted state all the way back into readable data. Think of it this way. If an AR model is that typewriter pressing one single key at a time, a discrete diffusion model is more like a master sculpture. It starts with a giant block of marble, which represents pure noise, and it chips away at the entire block simultaneously, until the final sequence of words is completely revealed.
And you can actually visualize the geometry of that state space, that exact sculpting process in action. When we start at time equals 1.0, we just have uniform noise. It's a completely random, uncoordinated gas, something nonsensical like the words blue moon. But as time runs backward towards 0, the probability mass shifts. The model smoothly interpolates. It concentrates its certainty away from the noise and onto valid data modes. It jumps from blue moon, maybe over to dark cloud, and finally converges on a highly probable, coherent phrase like red sunset at time 0.0. And the crazy part? It's doing this from multiple dimensions in parallel.
Section 3. Inside DiffusionGemma's architecture, let's look under the hood. To turn all that abstract math into concrete engineering, the DeepMind team adapted the massive Gemma 4 26 billion parameter mixture of experts model. DiffusionGemma uses what is called block autoregressive generation. So instead of generating one token, it processes an absolutely incredible 256 tokens at once. It treats them as a single canvas. First, a causal encoder processes your prompt and initializes the memory, the KV cache. Then the bidirectional decoder takes over the denoising framework at Inference. It denoises that entire 256 token canvas simultaneously, using bidirectional attention to look both forwards and backwards within the block. Once the canvas is totally clean, it gets appended to the context and the model seamlessly moves to the next block. Now, what's really interesting about this setup is a vital component called the DiffusionGemma sampler. Specifically, it's an entropy-bounded sampler. This is a dynamic sampling mechanism that stops the denoising process early, based entirely on the model's stepwise uncertainty. It uses a technique called temperature annealing, where the temperature drops from 0.8 to 0.4 during the process. This essentially forces the model to explore diverse options early on and then aggressively commit to high-confidence sequences as it refines. This adaptive stopping is exactly what makes the model so incredibly efficient. It saves vast amounts of computational effort. And because of that adaptive stopping, DiffusionGemma can dynamically adjust how many denoising steps it takes based on the actual complexity of the task it's been given. Depending on the benchmark, the step count fluctuates. For simple tasks, the model just stops early, saving computational effort and time. But for harder logic or complex math puzzles, it automatically expends more compute steps to ensure accuracy. It's a highly intelligent, automatic allocation of resources. Section 4, the two-stage training pipeline. So you might be wondering, how do you even train a beast like this without spending millions and millions in compute? Well, pre-training a diffusion model from scratch is prohibitively expensive. So the researchers actually bypassed it entirely. They warm-started the process with the existing Gemma 4 autoregressive weights. From there, they used a very clever two-stage process that required less than 10% of the original AR training budget. Step 1 is supervised fine-tuning, or SFT. This teaches the model bidirectional attention across those massive 256 token canvases. Step 2 is SDRL, sampler distillation and reinforcement learning. This is the critical phase that simultaneously maximizes the generation quality while significantly compressing the number of denoising steps needed. That's what unlocks the ultra-low latency.
Section 5. Inference optimizations and advantages. Let's look at the actual track results.
So the crucial point is how fast this actually runs when deployed for low batch size serving. When you break down the GPU time, a single step in DiffusionGemma takes 12.63 milliseconds. Now, yes, that is a 3.2x latency increase per step compared to standard AR. There are definite overheads in the mixture of experts layers, the sampling process, and the flash attention for mechanisms. But here is the absolute magic of the system. An AR model is only generating one single token in its 4 millisecond step. DiffusionGemma is generating 256 tokens in its 12 millisecond step. That massive output perfectly offsets the heavier forward pass. Because of that massive parallel processing, DiffusionGemma achieves a staggering output speed of 1,500 tokens per second. And guys, that is running on just a single NVIDIA H100 GPU. It's a phenomenal, complete step change improvement in generation speed for single requests. And this brilliantly illustrates the advantage when we plot it against the competition. When you look at the Pareto curve mapping generation quality against output decoding speed, DiffusionGemma establishes an entirely new Pareto frontier. It pushes the speed boundary way beyond prior text diffusion models and traditional AR models. And it does it without sacrificing the high intelligence you'd expect from a 26 billion parameter model. But the thing is, speed isn't the only benefit here. Text diffusion brings several really amazing practical advantages to the table. First is bidirectional reasoning. Because the generation isn't strictly causal, future tokens can actually inform and correct past tokens right there within the same block. It also allows for that dynamic adaptive computation we saw earlier, automatically spending more time on hard problems. And finally, it's absolutely fantastic for structured and constrained outputs, simply because all the tokens are evolving together simultaneously. To put that into perspective, let's look at a specific math reasoning problem. The prompt asks the AI to solve a tricky equation. A standard AR model forced to generate left to right commits to the wrong answer, like -1 in its very first tokens. As it generates its reasoning later in the sequence, it basically realizes it messed up. But it's too late. It just awkwardly appends a correction at the end. But with DiffusionGemma, because the reasoning and the answer co-evolve simultaneously across the whole canvas, it initially considers -1 as well, but then catches the error and self-corrects to the right answer, -25, in just 5 steps. The future tokens literally reach back and fix the past tokens.
Section 6. Limitations and the future. Let's bring this home.
Now, to be academically honest here, we do have to look at the trade-offs. The conversion to text diffusion does sacrifice some absolute benchmark performance on advanced reasoning when compared to the baseline AR model. You are trading a bit of absolute accuracy for that massive 5x speedup. But here is an incredible surprise fact. DiffusionGemma natively retains its original autoregressive capabilities. Because it shares the exact same transformer architecture as its baseline, you can actually just load the weights back to a standard AR pipeline and run it sequentially if you want to recover that max benchmark performance.
Which leaves us with a really fascinating question for the future of generative text. What is the ultimate potential of a dual-mode hybrid AI? One that routes requests between traditional autoregressive generation and text diffusion on the fly, purely based on latency constraints and task complexity.